So today we'll be going over the pre-lab lecture for Lab 7, just the titration of different acids. This lecture is mostly material from Chapter 15, which the lecture should be posted here pretty soon, so you can see my notes from there as well. On Chapter 15 that can aid your understanding of the material that's covered in this particular lab. I'm just going to go over the background and sort of how we're setting this lab up and what is to be done. So we're going to be doing titrations of acids and bases. You may have guessed as much from the title of the lab. And basically titration is just a way of determining the concentration of an unknown solution by reacting that solution with a measured volume of some standard solution, and then we can figure out with those two numbers, or three numbers that you sort of initially have, we can figure out what the concentration of our unknown solution is. And so if we use a pH meter to follow our titration, we can get a curve of the pH versus the amount of standard that is added in a particular solution. We can find out a number of things from the shape of the curve, and the two things that we're going to be after in this particular lab is we are going to be looking for an equivalence point, and that equivalence point is basically when we have stoichiometrically equivalent amounts of acid and base present that we've reacted. We've completely neutralized whatever the acid or base was in the unknown solution with some standard that we have present. And we can also, from looking at the curve, we can determine the type of titration. Is this a strong acid or a strong base that's being titrated? Is it a strong acid versus weak base, or is it a strong base versus weak acid? So we can determine a number of things from just looking at the curve. We can also, like I said early in this, that we can determine the concentration of that unknown solution. So that's something that you'll be doing as well. So the first one we're going to discuss is what a titration curve looks like for a strong acid and a strong base. So a common one to look at is just hydrochloric acid with sodium hydroxide to yield water and sodium chloride. The titration curve typically is going to look like something you see here on the left-hand side. We're adding a base as we move along, and so the pH increases towards 14 as we continue to titrate that base into the solution. So the setup would look something similar to what you've seen in the lab. You basically have a burette with the standard that we know the concentration, and that's going to contain a strong base, sodium hydroxide, and then our strong acid, which most likely is an unknown amount, is going to be in the Erlenmeyer flask below. So when we've added enough sodium hydroxide to neutralize all the acid that's present in that Erlenmeyer flask, we're going to be at the equivalence point. What do we have left when we're at this equivalence point? Well, when the reaction has concluded, we only have sodium chloride and water. Both of those species are not going to be considered acidic or basic, and so they're not going to continue to create H+ or hydroxide ions, and we expect that that solution is going to be at a pH of 7 as we've basically neutralized all the hydronium and all the hydroxide that's present. And so if we're looking for an equivalence point for a titration of strong acid and strong base, then we always expect that to end at a pH of 7 or have an equivalence point at a pH of 7. Another thing I should mention is that when we look at that equivalence point, you see it's in the middle of that sort of sharpest sort of slope upwards in our titration curve. And so it's always at the very center there. Another way that we can recognize it is that on the left-hand side before the equivalence point, if we were to look at the curve, it curves in a sort of counterclockwise fashion if we were basically to draw that curve. And when we go to the other side, past the equivalence point, the curve is moving in a clockwise fashion. And so when we see basically this curve change its curvature, that is called an inflection point. And that's another way that we can recognize where that equivalence point exists. So the next titration that we're interested in looking at is the titration of a strong base with a weak acid. This is actually the type of titration that you're going to do several calculations with in the lab. And so we're going to look at the titration of acetic acid with sodium hydroxide. That's going to yield sodium acetate and water. We know that acetic acid is a weak acid, sodium hydroxide being a strong base. When the reaction's gone to its equivalence point and we reacted all the hydroxide with all the acetic acid, we'll only be left with sodium acetate and water. The sodium does nothing, the water is going to be neutral, and the sodium acetate, or the acetate ion more importantly, is going to be the only thing that actually is going to contribute to the pH being either basic or acidic. And in this case, since it's a weak base, it's going to make the solution slightly basic. So if we go ahead and look at the titration curve that we would expect for that particular reaction, we're adding a strong base, and so we expect the pH to go up. We were initially adding it to a weak acid, and so that weak acid would have started at a pH less than 7. So that's where we start. The titration setup is going to look something like this, where we have the strong base in the burette, and we have the weak acid, probably with our unknown concentration of solution sitting in the Erlenmeyer flask. If all the strong base then reacts with the weak acid, we're left with that acetate ion, as I mentioned earlier. That leaves us just with acetate plus water, reacting to form with some amount of acetic acid and hydroxide. So yielding hydroxide ions, it's going to give us a basic solution at the equivalence point. And so we can expect that if we were to see an equivalence point in the basic sort of region, pH greater than 7, we'd expect that we were looking at the type of titration with a strong base and a weak acid. And again, you see that equivalence point happens in between on that steepest part of the curve there, and it's also where our curvature changes from, again, going from counterclockwise to clockwise in the top portion there. In the lab, you're going to need to calculate the expected pH at that equivalence point. And we're going to give you a more thorough example, or I'm going to give you a more thorough example of how to do that with the opposite titration when we're doing a strong acid with a weak base. Like I said, as long as you can understand how to do the titration or do the calculations for that titration that we're going to discuss in a moment, you should be able to get back to this one and figure out how to do the calculations for that. But if you're having any trouble with it, then don't hesitate to contact me, and we can go over it in more detail. So here we consider our titration of a strong acid, HCl, with a weak base, ammonium. Those two reacting to neutralize one another, we have the NH3 reacting with the HCl. When those fully react, we are left with NH4 plus chloride. Now, the weak base is NH3 to start, and HCl is our strong acid. What we are left with is only a weak acid. That chloride is not going to be acidic nor basic. It's not going to interact with the water to yield any hydronium ions or hydroxide ions. So we're just left with the weak acid, NH4+. So we will get a titration curve that looks something like this. Because we started with a weak base, we'll have a pH that's initially greater than 7, and we'll see the reaction, the pH of the reaction, or I should say of the solution, go downwards as we add more and more of the HCl. So in this case, notice that in the burette we have hydrochloric acid, and in the Erlenmeyer flask we have the NH3 present. So when we react all of the acid with a weak base, we will only have NH4+ present and contributing to the acidity of our solution. And so we can expect the reaction is going to be this ammonium ion, NH4+, reacting with the water to yield NH3 and hydronium ion. So if we consider, if you had, for our example, how would we do two things: predict the amount of HCl necessary to reach the equivalence point, and to also predict the pH at which we will see the equivalence point. So if we're doing that problem, the first thing we actually want to do is we want to figure out how much HCl we expect to add. You've done some of the titrations in the past in the lab. It's good often to do a rough calculation in the beginning just to see what you expect to be that equivalence point, because it sneaks up on you. You see how fast or large the slope is at those equivalence points. And so just a drop can change the pH drastically in those regions. And so if we have an estimation of where that window is, we'll do a better job of perhaps calculating the or sneaking up on that equivalence point and getting an accurate titration. So we have the reaction of NH3 plus HCl to give us that ammonium and the chloride, and that's the neutralization reaction we're interested in. We know we had 25 milliliters of this 0.1 molar NH3 that's sitting in the Erlenmeyer flask, and that's what we start with our calculation. From there we can figure out the number of moles of NH3. We know those react in a 1-to-1 fashion according to the balanced equation we have above. And then we know that we are reacting it with 0.0 or that 0.3 molar HCl. So if we look at the fact that we get 0.3 moles of HCl per 1 liter, and then switch that into milliliters, units all being canceled there, we are left with 8.3 milliliters of HCl are expected to be necessary in order to reach that equivalence point. So now our last task of figuring out what will the pH be at that equivalence point. So our initial concentration was 0.1 molar of NH3. By the time that you've reached the equivalence point, you're still going to have the same number of moles present. But the difference now is that you have 25 milliliters plus you've added that 8.3 milliliters from the strong acid HCl. And so this is going to give us a new concentration for NH4 plus at the equivalence point when everything's reacted. We can calculate what this new concentration is using just the M1V1 equation that we used a lot in the first semester. So M1V1 equals M2V2. I rearranged that for the molarity at that equivalence point after I added 33.3 milliliters. You should expect that the concentration has decreased because you've added some volume, but you've not changed the number of moles that are present. So our new concentration would end up at 0.076 molar. We have the ammonium ion reacting with water to yield NH3 and hydronium ion at the equivalence point. All we're left with at that equivalence point is just the ammonium ion, which is acidic. And so we expect the equivalence point when we do a titration of a strong acid with a weak base, we should expect an equivalence point that has a pH that is less than 7. If we want to figure out what the concentration or what the pH is, then we need to set up an ICE diagram. And so I plug in my initial values, which is just the 0.076 molar of the NH4 plus, the new concentration we just calculated. I plug in the 0 values for the NH3 initially and the H3O plus. And then since they're all related by a 1-to-1 stoichiometric ratio, it's just a minus X under that column for the change. A plus X in the NH3 and an H3O plus, we have a plus X as well. Summing those two previous entries, we end up with 0.076 minus X for the ammonium concentration at equilibrium, and X for the NH3 and H3O plus. Typically, when you do one of these problems, you are going to be given if NH3 is more popular than NH4 plus, say, and so often you'll be given the base dissociation constant, Kb. And so what we need in order to figure out this particular problem, because this is looking at the Ka, or the acid dissociation constant for NH4 plus, we have to relate those two. And as I said, if you were to look through chapter 15 lecture, you'll see our discussion of this in more detail. However, what you will see there is that Ka times Kb gives you Kw. And so since we know Kw to be 10 to the minus 14, we can algebraically rearrange that equation such that Ka equals Kw over Kb, and then we are left with the Ka value, or the acid dissociation constant, for NH4 plus. And so that is just a common thing that you often see. Okay, so we plug in our values at equilibrium, and that gives us just the products over the reactants. And if we look at plugging in our values that we calculated, we'll end up with x squared over 0.076 minus x. We're looking at the dissociation of a weak acid, and it's got a constant of 5.6 times 10 to the minus 10, some number that's exceedingly small. And so we expect this reaction to favor the reactants. If that's the case, then we should be well within our estimates to go ahead and eliminate that minus x term on the denominator there, make the approximation that it's just x squared over 0.076. With a little bit of rearrangement, we can solve for x, and that just becomes square root of 0.076 times the acid dissociation constant Ka. That leaves us with a number of 6.52 times 10 to the minus 6. This is also equivalent to the ammonia concentration and the hydronium concentration. Here, we're interested in the hydronium concentration. If we know the hydronium concentration to be 6.52 times 10 to the minus 6, then I can plug it into the pH, and I can go ahead and do the negative log of that concentration, yielding 5.19. And that is what we would expect, where we would expect the equivalence point to occur in this particular reaction. So hopefully that gives you a rundown on some of the calculations you'll be doing in this lab. Don't hesitate to contact me by email or Google Meet, and we can discuss how to do any of the calculations in your lab. Hope this was helpful.